There exists, beyond the furthest galaxy we can see, beyond the cosmic microwave background that marks the edge of our observable universe, something we cannot name. Something vast. Something pulling. For decades, we have mapped the heavens with increasing precision, charting the movements of galaxy clusters across billions of light-years, confident in our understanding of cosmic motion. We expected to find randomness, the gentle chaos of expansion, each galaxy cluster drifting away from every other in the great unfolding that began 13.8 billion years ago. But we found something else entirely. We found agreement. We found synchronization. We found hundreds upon hundreds of galaxy clusters, each containing thousands of galaxies, each galaxy harboring hundreds of billions of stars, all moving together in the same direction at over 2 million miles per hour, as though caught in an invisible current flowing toward a region of space we cannot observe, toward something beyond the horizon of light itself. This is not the motion we expected. This is not the gentle dispersal of the Big Bang. This is something older, perhaps. Something larger. Something that exists in a place our telescopes cannot reach, in a realm where light itself has not had time to travel to our eyes since the beginning of everything. And yet its influence reaches across the entire visible cosmos, tugging at the very fabric of space-time, pulling galaxy clusters like leaves on a river we are only beginning to understand exists. We call this phenomenon dark flow, though the name itself is an admission of ignorance, a placeholder for a mystery that threatens to rewrite our understanding of cosmology itself. What could possibly exert such force across such incomprehensible distances? What lies beyond the edge of everything we can see? The discovery emerged not from a single eureka moment but from the patient accumulation of data, from thousands of observations compiled over years by scientists studying the cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space. When we measure this radiation with sufficient precision, we find tiny temperature variations, hot spots and cold spots that differ by mere millionths of a degree. These variations tell us about the distribution of matter in the early universe, about the seeds that would eventually grow into galaxies and clusters. But embedded within this data, when analyzed through a technique called measuring the kinematic Sunyaev-Zeldovich effect, scientists found something peculiar. Galaxy clusters were creating systematic distortions in the microwave background, distortions that revealed motion, coherent motion, flow in a single direction across vast swaths of the sky. The team that first identified this anomaly, led by Alexander Kashlinsky at NASA's Goddard Space Flight Center, published their findings in 2008, and the astronomical community responded with immediate skepticism. Such large-scale coherent motion violated our most fundamental assumptions about the universe. According to the cosmological principle, the universe should be homogeneous and isotropic at the largest scales, meaning it should look roughly the same in all directions, with no preferred orientation, no cosmic axis, no universal flow. The Big Bang should have distributed matter and energy evenly, or at least randomly, creating expansion but not organized movement toward a specific point or away from a specific source. Yet here was evidence suggesting that an enormous volume of space, containing hundreds of galaxy clusters spread across 2 to 3 billion light-years, was drifting together, moving as a unified whole toward a point in the sky between the constellations Centaurus and Vela, toward the southern celestial hemisphere, toward a place astronomers began calling the dark flow region. The implications were staggering. If this motion was real, if it persisted across such distances, then something beyond our observable universe must be influencing it. The observable universe, remember, is not the entire universe. It is merely the region from which light has had time to reach us since the Big Bang. Beyond that sphere, which extends roughly 4 to 6.5 billion light-years in every direction due to the expansion of space, there exists more universe, perhaps infinitely more, filled with galaxies and structures we will never see because their light has not yet reached Earth and may never reach Earth if cosmic expansion continues to accelerate. We are trapped inside an expanding bubble of visibility, surrounded by an unknowable vastness. And now, evidence suggested that this unknowable vastness was not empty, not inert, but contained something massive enough, dense enough, gravitationally significant enough to pull visible matter toward it across billions of light-years. What could it be? The hypotheses ranged from the conservative to the cosmologically revolutionary. Perhaps, some scientists proposed, we were witnessing the gravitational influence of an enormous supercluster of galaxies just beyond our cosmic horizon. A structure so massive it had not yet come into view but whose gravity reached across the boundary of observation. Such a supercluster would need to be extraordinarily dense, far more massive than any structure we have observed within our visible universe, but not impossible according to some models of cosmic structure formation. Others suggested we might be seeing the remnant influence of density variations from the inflationary epoch, that brief moment immediately after the Big Bang when the universe expanded exponentially, potentially creating large-scale inhomogeneities that still affect motion today. These variations, frozen into the fabric of spacetime during inflation, could create pressure differences that manifest as bulk flows of matter across cosmic scales. But the more exotic possibilities captured imaginations with greater force. What if, some cosmologists asked, our universe is not alone? What if the Big Bang that created our observable cosmos was merely one event among countless others, one bubble nucleating in an eternal inflation process that creates universe after universe after universe, each with potentially different physical laws, different constants of nature, different dimensions of space and time? In such a multiverse scenario, our universe might be gravitationally interacting with neighboring universe bubbles, feeling their pull across the membrane that separates one reality from another. The dark flow could be the tug of another universe, close enough in the higher dimensional space that contains all universes to exert measurable influence, pulling our galaxy clusters toward it like the moon pulls Earth's oceans into tides. We would be feeling, quite literally, the gravity of another creation, another Big Bang, another entire cosmos existing alongside our own in a space our mathematics can describe but our instruments can never reach. Or perhaps, and this hypothesis ventures even further into the speculative, the dark flow represents something left over from before the Big Bang itself. Some versions of cosmological theory propose that our universe emerged from the collapse of a previous universe, that the Big Bang was actually a big bounce, a transition point in an eternal cycle of expansion and contraction. If this were true, then certain large-scale structures or density variations from the previous universe might have survived the transition, imprinting themselves on our current cosmos. The dark flow might be an echo, a gravitational fossil from a universe that existed before ours, before time as we understand it began, a memory written in the motion of galaxies. The scientific process demanded verification. Independent teams began analyzing the same data, applying different statistical methods, searching for errors, testing the robustness of the signal. Some found confirmation, detecting the same coherent motion in their analyses. Others found nothing, suggesting the signal was an artifact of data processing, a mirage created by systematic errors in how the cosmic microwave background measurements were calibrated. The debate grew heated, as scientific debates often do when fundamental assumptions are challenged. Papers were published supporting dark flow. Papers were published refuting it. Conferences featured presentations from both camps, each armed with sophisticated statistical analyses, each convinced of their interpretation. The question remained open, unresolved, hanging over cosmology like a puzzle piece that did not fit the picture we had assembled. Then came more data. The European Space Agency's Planck satellite, launched in 2009, provided the most precise measurements of the cosmic microwave background ever obtained. When the Planck team analyzed their data for signs of dark flow, they found no significant evidence supporting it. Their measurements suggested that any bulk flow was much smaller than Kashlinski's team had claimed, possibly consistent with zero when accounting for uncertainties. This appeared to be a decisive refutation, a case closed by superior data. Many scientists moved on, satisfied that dark flow had been revealed as an illusion, a cautionary tale about jumping to exotic conclusions before extraordinary claims had been sufficiently verified. But Kashlinsky and colleagues stood by their findings, arguing that different analysis techniques and different ways of filtering the data could explain the discrepancy, that the Planck results did not definitively rule out a more modest but still significant flow. And so the mystery persists, unresolved, living in that uncomfortable space science sometimes occupies between discovery and dismissal, between revolution and error. The truth, as it often does, may reside somewhere between the extremes. Perhaps there is a bulk flow, smaller than initially claimed but still real, still significant, still requiring explanation. Perhaps our models of cosmic expansion need refinement, subtle adjustments to account for large-scale motions we had not previously considered important. Or perhaps we are witnessing something genuinely new, something that demands we expand our conception of what exists beyond the visible edge of creation. Consider for a moment what it means to live inside an observable universe, to be confined by the speed of light to knowledge of only a finite sphere of existence. Every direction you look into the night sky, your vision terminates at the same distance, at the surface of last scattering where the cosmic microwave background originates, at the moment when the universe became transparent to light for the first time, roughly 380,000 years after the Big Bang. Beyond that surface, the universe continues, certainly, filled with galaxies and stars and perhaps planets and life, all evolving according to the same physical laws, all aging along the same cosmic timeline. But you will never see them. Their light will never reach you. The expansion of space has carried them beyond the horizon of causality, beyond the realm of possible observation, into a region that is real, that exists, that matters, but that remains forever unknowable through electromagnetic radiation. This is a humbling realization, one that places humanity in yet another peripheral position in the cosmic hierarchy. Copernicus removed us from the center of the solar system. Hubble showed us our galaxy was one among billions. Modern cosmology now tells us we cannot even see most of what exists, that we are trapped inside an island of visibility surrounded by an ocean we can never cross. And if dark flow is real, that ocean is not empty and still. It moves. It contains currents. It harbors structures massive enough to influence the shores of our visible world. The mathematics of cosmic expansion, described by general relativity through what we call the Friedmann equations, predict a universe that expands uniformly in all directions from every point. Space itself stretches, carrying galaxies away from each other, not because they move through space but because space itself is growing between them. This expansion should create a particular pattern of motion. The farther away a galaxy is, the faster it should be receding from us, a relationship quantified by Hubble's constant. But this recession should be radially symmetric, pointing away from us in all directions equally, because we do not occupy a special position. Every observer in every galaxy should see every other galaxy receding according to the same expansion law. There should be no net drift, no organized flow toward or away from any particular direction. The dark flow, if real, violates this expectation. It suggests an asymmetry, a preferred direction, a cosmic anisotropy that standard cosmological models struggle to explain. Some researchers have proposed that what we are seeing might not be external influence at all but rather an indication that the universe itself is rotating at the largest scales. A rotating universe would create exactly the kind of coherent motion detected in the dark flow observations, with matter swirling around a cosmic axis like water circling a drain, though on a scale almost impossible to visualize. Such rotation would have profound implications. It would mean the universe possesses angular momentum, that it spins, that it has an orientation in some higher dimensional space. Where would such rotation come from? It would need to have been imprinted at the moment of creation, built into the initial conditions of the Big Bang itself, or perhaps inherited from whatever came before if our universe emerged from a previous state of existence. Current observations place strict limits on how fast the universe can be rotating based on measurements of the cosmic microwave background. Limits that seem to rule out rotation as an explanation for dark flow unless the rotation axis is oriented in a very particular way that makes it difficult to detect through other means. Another possibility involves the nature of cosmic expansion itself. We know the expansion is accelerating, driven by something we call dark energy, a mysterious component that comprises roughly 68% of the total energy density of the universe. Dark energy behaves like a property of space itself, creating a repulsive gravitational effect that pushes galaxies apart at ever-increasing speeds. But what if dark energy is not perfectly uniform? What if it varies slightly from place to place, creating regions where space expands faster or slower than average? Such variations could create pressure gradients, differences in the effective density of dark energy that would cause matter to flow from regions of higher dark energy density toward regions of lower density, much like air flows from high pressure to low pressure systems in Earth's atmosphere. If a region of anomalously low dark energy density existed just beyond our cosmic horizon, it might pull galaxy clusters toward it, creating the appearance of a dark flow without requiring any exotic structures or multiverse interactions. Testing these hypotheses requires better data, more precise measurements, and observations across multiple independent methods. Astronomers continue to refine their techniques for measuring galaxy cluster velocities, using not just the kinematic Sunyaev-Zeldovich effect but also direct observations of galaxy redshifts, gravitational lensing measurements, and the distribution of matter traced through X-ray emissions from hot gas in galaxy clusters. Each method has its own systematic uncertainties, its own potential sources of error, but together they can provide cross-confirmation, building a more robust picture of cosmic motion. Several large-scale surveys currently underway, including the Dark Energy Survey and observations from the Vera Rubin Observatory when it reaches full operation, will map millions of galaxies with unprecedented precision, allowing astronomers to search for bulk flows and test whether the dark flow signal persists in independent datasets. What makes this mystery particularly fascinating is how it connects to the deepest questions in cosmology. If something beyond the observable universe is influencing motion within it, then we are forced to contemplate the nature of cosmic boundaries, the relationship between the visible and the invisible, the known and the unknowable. Philosophy and physics converge here, at the edge of measurement, at the limit of light. Medieval philosophers debated how many angels could dance on the head of a pin, questions that seemed profound at the time but ultimately proved unanswerable because they lay outside the realm of empirical investigation. Is the question of what lies beyond the cosmic horizon similarly metaphysical, forever beyond science's reach? Or can we infer, through indirect effects like dark flow, something about regions we can never directly observe, using the same logic that allows us to deduce the existence of black holes from the motion of stars orbiting invisible points, or to confirm the existence of dark matter from the rotation curves of galaxies? The answer may depend on whether the universe is finite or infinite. If the universe is infinite in extent, then beyond our observable sphere lies infinite space containing infinite galaxies arranged in every possible configuration. Statistical arguments suggest that in an infinite universe, everything that can happen does happen, infinitely many times, including exact copies of Earth and exact copies of you reading these words, scattered across the endless expanse separated by distances so vast that the word distance loses meaning. Such infinity creates philosophical paradoxes and makes prediction impossible because infinite possibilities dilute probability to meaninglessness. But it also means that arbitrarily large structures must exist somewhere, including structures massive enough to create flows like the one potentially observed, structures that might be statistically unlikely in any finite volume but guaranteed to exist given infinite space. If instead the universe is finite, curved back on itself in higher dimensions like the surface of a sphere is finite despite having no edge, then the total amount of matter and energy is limited, and the kinds of structures that can exist are constrained by that total budget. A finite universe might still extend far beyond our observable patch, but not infinitely far, and the regions beyond our horizon would eventually loop back around, meaning that in principle, if we could wait long enough and if expansion did not accelerate indefinitely, light from those distant regions might eventually reach us, completing a circuit around the entire cosmos. In such a universe, dark flow might represent gravitational influence from structures on the far side of cosmic space, distortions in spacetime's curvature that propagate across the closed topology, creating flows that seem to come from beyond the horizon but actually originate from regions that are distant but finite. The search for answers leads us deeper into the mathematics of spacetime itself, into Einstein's field equations that describe how matter and energy curve the fabric of reality. These equations are elegant in their symmetry, describing a universe where geometry and physics are inseparable, where the presence of mass tells space how to bend and the curvature of space tells matter how to move. But the equations are also extraordinarily difficult to solve except in highly simplified cases. When we model the entire universe, we must make assumptions, invoke symmetries, reduce the impossible complexity of trillions of galaxies each pulling on every other through gravity into manageable approximations. We assume homogeneity, we assume isotropy, we treat the cosmos as a smooth fluid at the largest scales, ignoring local variations. These assumptions work remarkably well for describing the overall expansion history, the evolution of the universe from the Big Bang to the present, but they may fail to capture subtle large-scale flows, organized motions that emerge from asymmetries in the actual distribution of matter. Modern supercomputer simulations attempt to model cosmic structure formation with fewer assumptions, evolving billions of particles forward through time according to gravitational and hydrodynamic forces, watching as initial tiny density fluctuations grow into the cosmic web of filaments and voids we observe today. These simulations reproduce many features of the real universe with stunning accuracy, creating virtual galaxies that look and behave like actual ones, forming clusters in the right places at the right times. When researchers analyze the velocities of structures in these simulations, they find that bulk flows do emerge, coherent motions on scales of hundreds of millions of light-years driven by the gravitational attraction of massive structures. However, the flows predicted by standard simulations are generally smaller than what the dark flow observations suggested, typically a few hundred miles per second rather than over 2 million, and they tend to decrease on the very largest scales as the universe becomes more homogeneous. This discrepancy, if the observations are correct, hints that something in our standard cosmological model may be incomplete. Perhaps the missing ingredient is a better understanding of how the universe began. The inflationary paradigm, which proposes that the universe underwent exponential expansion during the first tiny fraction of a second after the Big Bang, successfully explains many features of the cosmos, including why space appears flat, why the cosmic microwave background has nearly uniform temperature, and why we see the particular pattern of density fluctuations that seeded galaxy formation. But inflation also makes a startling prediction. Our observable universe represents only an infinitesimally small patch of a vastly larger region that inflated together, and beyond that region may lie other patches that inflated differently, or stopped inflating at different times, creating a patchwork multiverse of bubble universes each with potentially different properties. If we live in such a multiverse, then the region just beyond our cosmic horizon is not random but structured, potentially containing enormous variations in density or energy that could influence motion within our visible patch. The dark flow might be our first indirect glimpse of this larger structure, the first observational hint that inflation created more than just our lonely bubble, that we are part of something incomprehensibly vaster. Yet we must remain cautious. The history of astronomy is filled with phenomena that seemed revolutionary when first detected but later proved to be misinterpretations or instrumental artifacts. The canals of Mars, once thought to be evidence of alien civilization, turned out to be optical illusions created by the tendency of the human eye to connect random features into patterns. Pulsars, when first discovered, seemed so regular and artificial that astronomers briefly considered they might be signals from extraterrestrial intelligence before recognizing them as rapidly rotating neutron stars. Science advances through a cycle of observation, hypothesis, testing, and revision, and extraordinary claims require extraordinary evidence before the scientific community accepts them as established fact. The dark flow remains in the hypothesis stage, intriguing but unconfirmed, awaiting the verdict of better data and more comprehensive analysis. What remains certain is the profound sense of mystery these observations evoke, the reminder that despite all our telescopes and equations, despite mapping the cosmos to within a fraction of a second after its birth, we remain fundamentally ignorant about what lies beyond our small sphere of visibility. 95% of the universe consists of dark matter and dark energy, substances we have never directly detected, known only through their gravitational effects. The remaining 5%, the ordinary matter that makes up stars and planets and our bodies, is itself mostly invisible, hidden in clouds of gas too diffuse to shine or locked away in black holes beyond the reach of light. And now, potentially, we confront evidence of influence from beyond the cosmic horizon, from regions we can never see, governed by physics we can only infer. Humility, it seems, is the appropriate response, a recognition that our knowledge, however impressive, remains a tiny island surrounded by an ocean of unknowing. As you lie here in the darkness, consider your place in this vast and mysterious cosmos. You exist on a rocky planet orbiting an ordinary star in the outer suburbs of a typical galaxy, one of hundreds of billions of galaxies scattered across the observable universe, all of them potentially caught in a slow drift toward something beyond the edge of everything we can see. The atoms in your body were forged in the cores of ancient stars that exploded billions of years ago, scattering their enriched material into space where it eventually condensed into new stellar systems, including our Sun and Earth. You are, quite literally, made of stardust, animated stardust contemplating the universe that created it. And that universe, it seems, is stranger and larger and more connected than we ever imagined, filled with forces and structures we are only beginning to detect, moving according to patterns we are only beginning to understand. The dark flow, real or illusory, serves as a reminder that the cosmos still holds secrets, that the work of science is never complete, that each answer generates new questions in an endless progression toward deeper understanding. We may never know with certainty what lies beyond the cosmic horizon, never confirm whether other universes exist in parallel dimensions, never determine whether our universe is finite or infinite, rotating or static, unique or one among countless others. But we can continue to observe, to measure, to calculate, to test our ideas against reality, expanding the boundaries of knowledge one careful observation at a time. And in that process, in the patient accumulation of data and the rigorous testing of hypotheses, we honor our deepest human impulse, the desire to understand, to know, to place ourselves in context against the vast backdrop of existence. Sleep now, knowing that you are part of something immeasurably large, something moving through space toward a destination unknown, carried along with galaxy clusters and dark matter and all the visible matter in the universe on a journey that began nearly 14 billion years ago and continues still. You are a passenger on spaceship Earth, which orbits a star traveling through the Milky Way, which moves through the local group of galaxies, which drifts with the Virgo supercluster, which may itself be flowing with hundreds of other clusters toward the Great Attractor or beyond, toward whatever mystery waits in the darkness beyond the edge of light. Rest easy in your smallness, in your insignificance, in the magnificent improbability of your existence. You are the universe contemplating itself, consciousness arising from matter, asking questions about origins and destinations, about what pulls us and where we are going. And that, perhaps, is answer enough for now.